Causal Islands. I'm Andrés Cuervo, and I work with Omar Rizwan, uh, Brooklyn, New York, on Folk Computer, which is an open source physical operating system. So I'm actually using a small version of Folk here, and I want to explain sort of the motivation behind what we're building. So when you typically think about a computer, you think about a laptop or a desktop set in some physical desk, and the way that we talk about computers is that they can organize all of our information. But if you actually look at how people use computers in the real world, or use their physical workspaces, they're often writing down physical notes. They're often using their entire bodies to work with large vertical surfaces. If you're doing sort of deep knowledge work, you often have a stack of books. You have a set of papers around you. You have an iPad and a phone and a computer all working together. And so if you take that as the basis of your work, then you realize that your computer actually isn't including all the physical things around you that you use to do your work. So if we start again and we consider what a computer could be, then we can start with our physical working space, and we can start with a printer. So we need a way to physicalize what we're programming, right? And we can print out the things that we're working on. We can add a webcam to this system so that we have a way of adding input into our system. And we can add a computer. We can attach some printed markers to our printed out programs. And what that enables us to do is attach code. So Folk Computer is also Folk is a language that we've written that makes it very easy to literally write programs that do work in the real world. So this program, for example, says wish this is outlined green and wish this is labeled hello world. So this particular setup that I'm building, that I'm illustrating here, was built to take input from the real world and projection map visuals back out. But you could imagine folk enabling sort of any arbitrary physical workspace to do a bunch of different things. So you could attach an IR camera, or you could have an audio-only version. The real magic of folk is that we're building a system that can take physical input. So we can keep going. We can keep adding. And now we have a way of getting input into our digital program, but we need a way to get output back. So we can add another little box that's a projector, and the projector can hit all the objects that are on our desk. And so now we have a way of actually fulfilling the program these wishes that are in our system. So we have, just to review, we have our physical input coming from the desk. We have our webcam talking to our computer. We have our computer talking to our projector, and now we can actually display. We can highlight green and add some text to our physical printed out programs. And this is not just a theoretical cute illustration. In our office in Brooklyn, we work this way every day. So we print out our physical programs, and we can display the results in real time next to whatever we're working on. And the way that we create new programs in this system, so to review, the way that we typically see computers marketed to us is as these sort of clean interfaces with trapped behind screens. And when you take a look at, try resetting this. So when you sort of go looking for examples of how people work in the real world, this is a great shot of Stuart Brand working on the book How Buildings Learn, and he actually built himself a studio with magnetic walls so that he could put chapters up and take them down and work on them in sort of these stacks and piles. So when you think about working on a big piece of media, like Andy Matuszczak often does, oftentimes the screen feels like a constricting little rectangle, and you have to you have to sort of splat out your notes onto a physical desk. And if you look at the Wikipedia page for the word research, what you see is this large desk, and it's filled with a archive of card boxes and a stack of notes and a little notebook that sort of keeps an index of all the indexes. And the actual laptop here represents the final output of what you're doing, right? I can't actually capture, or it's not sort of the most useful way to think about the work that you're actively doing. So there are people who are trying to build approaches to new computers that you think might solve these problems. So this is a picture of the Meta Quest, and this is the Apple Vision Pro, and they're sort of acknowledging that people think in 3D, right? Like an optimal way to use computers is to work in a physical space and sort of be able to move your whole body. But the thing that this lacks is the ability to actually touch what you're doing, right? So you can't build up this sort of secondary sense of where, for example, your physical notes are, right? You can't think about, oh, it's on that fourth page, that I left by my nightstand. And even more crucially, you can't build up physical interfaces where you can actually do real work. So you don't have any physical sense memory for the sort of inputs that you're putting into this system. And it's sort of completely disembodied. There are other systems that are sort of rely on new physical technologies that allow you to work, for example, in a room with a lot of sunlight. But those systems are still sort of, while interesting sort of physical artifacts, they're still living in this closed world of apps. And so you have this dichotomy, right, where you have spatial computing tools that like VR and AR tools that are interesting and sort of recognize the power of physical layout, but they're literally intangible. They're not physical. And you have custom computers, alternative computing technologies that are useful physical tools, but they're still programmatically isolated. So folk computer, when you put down a program, the piece of paper is not acting as a metaphor, right? It's like it literally is triggering this animation to move from where we've programmed our piece of paper to originate from. And the way that we make new programs in this world is by projection mapping an actual Bluetooth keyboard. So I have an example here. So we can attach a program to this, like this, and we can type out our code directly onto the surface, and we can print out new programs from there. So this is an example of a little mini receipt printer, and it's useful for this sort of portable system. But in our studio setup, we actually print out 8.5 by 11 standard US letter paper programs. And so we attach this marker, we attach this code, and we save the code that's running, that is supposed to run in association with our programs. So one of the most useful benefits of actually printing out your programs is that your interface is now wherever the program is physically on the table. So there's a program on this table in this image that actually connects all of these programs together. And this is a real-time way of inspecting where all your programs are and how they're related to each other. So now your interface is not some abstract thing. It's not a rectangle that you have to move around in space, or an indirect object that you have to click and drag, but rather it's a physical thing that you can fold and move and stack on top of each other in order to keep track of your version history. So now that we have a system for getting physical input into our programs, we can start writing programs that actually do work on the real world. So if you want to make an animation in this system, then you simply write a program that takes slices of camera input and puts them together at the end. So this little jumping animation is actually coming from this person whiteboarding down each of the keyframes here. And you could imagine a program that takes this and then uploads it and saves it to your laptop or emails it to somebody. So so Folk always has a webcam running above your working space so that you can actually save the programs that you're working on. So you can define a program that shows you the preview of the webcam, and then you have this other little program that can save that state. And it's acting as a button because I've folded it in sort of 5 sections, and so this clever little origami hinge actually means that my button is just a normal program that physically comes together. So there's actually no digital state that has to be saved, and I can just rely on the physical world changing my digital artifacts. And buttons can do any sort of display, so we can display a Mega Man sprite, for example, with one line of code, and do interesting work that way. We can again operate on our physical world, not using the markers exclusively. So here we're detecting any dark circle that's in the working area, and that defines the ending value for a slider. And so one of our friends, Naveen, is an open source contributor to the Folk project, and he's been playing around with this sort of physical interface for digital sliders. And our friend Cristobal put all these tools together to create a research gallery prototype. So you have a printed out paper that you're reading, and you really want to save certain sections of it. So he printed out his own hands and made that a view selector for a section of the camera, and then created this other button that intersects with that camera tool, and then it saves it to a list on the right. And so again, you can imagine saving this whole state together and sort of doing OCR on it and leaving it for review later. But the cool thing is that it remembers where all of your physical state is, right? So you have a better sort of sense memory than just an abstract selected PDF text, for example. And so I didn't actually hook up the audio today, but this should suffice. So, or let me turn it down for a second. So this person, Jesse Grossen, is another open source contributor at the Recurse Center in Brooklyn, and has set up a version of Folk that is able to communicate with Super Collider, which is a sound engine for creating in real-time sound programs. So each one of these paper buttons has a program that's written on it to say, wish this plays sound A, or wish this plays note A, for example. And so I can let this play. Yeah, and so this is mimicking a piano, but you could easily imagine swapping this out for any sort of digital synthesized sound, and you can begin to imagine a world of paper instruments that are able to do arbitrary DJing. No, not yet. We're thinking about it, and so. So again, the folk computer doesn't have to work just exclusively on these markers. So here's an example of our friend Jacob Hype, who made a system that is able to recognize the brightest point on a wall, and so from very far away you can use a laser pointer to trigger a program and display some text next to it. And so folk computer keeps itself running by taking contracts to build tools in the real world. So this is an example of a CNC machine. It's like a 3D printer, but in reverse. So instead of adding material, you put a block of material and it carves the material out, right? But this is a pretty expensive operation. It's if you have a sort of piece of wood that you're trying to carve, you want to know with precision that your design is going to work when you actually send the robot to do its carving. And so we got a commission to work on a system that is able to projection map the design with millimeter level accuracy onto your piece of wood. So folk computer is able to actually calibrate and register where your material is and preview your design. And so this is actually printing out one of our April tag markers onto a piece of wood. And this is showing a more precise illustration of being able to hit a very small design on a small piece of wood. Yeah, so folk is able to open up new possibilities in the real world. So folk is an open source operating system, and we are majority funded by contracts that we get to work on real world tools, and we have smaller contributors on our GitHub. And we encourage people to build their own folk systems. So we've open sourced not only our software, but also our recommendations for all of our physical hardware and the hard-fought knowledge of how to mount projectors vertically over your system. But we also support people building non-visual systems, like audio systems, for example. So we have a community of about 26 people who have set up folk in their either in spare rooms in their offices or in their personal home offices. And this is a listing of some of the people around the world who have set up folk in the last couple of years. And the hope is that as folk grows more capable, we should be able to support not only bringing physical tools into your digital world or digital tools into your physical world, but actually meeting you with wherever you are. So if you're a scientist who is working with chemicals and you know that these two particular things shouldn't ever mix, and you want to be able to dynamically display that when they get too close, then you should be able to do that. You should be able to set up folk and write a small physical tool, a small digital program that is able to monitor where your objects are and warn you about mixing things. We should be able to build programs like crystal balls where you are reading a physical book, or you take out your notebook and you're able to save state or be able to project annotations onto whatever you're working on in the real world. We should be able to support people building video games right in the physical world, or augmenting tabletop games. We want to support people doing simulations in the real world. So oftentimes simulations are one of these things where there's not enough. The advantage of the computer is that you can't think in real time about all the things that you're trying to keep track of, right? But having the physical affordance of being able to move around, for example, tokens in a simulation, or to keep a binder of simulations is like a really useful affordance. And eventually, folk should also be able to seamlessly integrate your other digital tools. So, for example, like one of my long-held dreams for folk is that it will hopefully in the next year be able to support you being able to literally pour data down from your phone and onto a physical table. So this looks like being able to stream a URL onto the table and sort of pour out a web browser, or be able to flick across a photo from your phone onto the table and make it very large, make a physical edit, and then move it back onto your phone. So you might have noticed that I've been flipping cards over here. So let me actually move this back. So these slides have been projected today, or been controlled today by this little gadget I have here. So it's in this pink box is a small projector, a small camera. Yeah.
Would you mind staying that handheld microphone? Right to the side, too. Yeah, right there. Yeah, just hold the button. There we go.
Okay. So is this good? Oh, sure. Okay, so Folk, we hope that Folk can support all of these uses. And so these slides today have been controlled by my stack of actual cards here that were printed out. And they've been projected and controlled by this little pink gadget. So it's a 3D printed gadget that is able to run Folk completely by itself. So it's a Raspberry Pi 5 and a mini projector with a little Raspberry Pi camera on the front. And I can actually display my slides. There we go. I'm Folk program number 59. So when I actually tilt this or twist this, it actually changes the way that the program appears on my projected slides. So I can actually give you a technical tour of how this is all working. So first thing to know is that you can actually see my slides, or see what the gadget sees when I refresh this page. So I'm gonna put my little receipt printer here and refresh, and you can see that it's a tiny little cat printer. So the way that this works is that there is a, let me start with this. So this gadget is called Gadget Red, and so it's available on the Wi-Fi. And when I go to this page over here, give it a second to load, you can actually see a statement of a library of all the statements that Folk is running. So if we take a look at this first one, we can see that the sort of kernel of this whole environment actually begins by defining what a program is. So the Folk language is built up of claims and wishes. And a claim enters a statement into the database. The database reacts to that entry. And then a win is a mechanism for capturing or for responding to statements that are true in the system. So if you remember, I have my my slide program on this table, and so I'm on slide number 60. So I can actually look for the program. I'm slide 60, and you can see the whole sequence of statements that led to recognizing and then projecting my program. So you can actually see that program number 72 is claiming that it is slide 60. And a more useful, or well, a more interesting visualization of sort of everything that's happening here is available over here. So I can see, instead of just seeing it as a linear list, I can see this very large graph.viz of all of my statements. So if I search for the same thing, we can see in this little section of the execution graph, we can see the same program is outlining itself gold, and it triggers a bunch of other statements that get sent to my slides in order to change what's being displayed. So I can go back to that last page and show you how to make a program without a physical keyboard here. So I can write, can say wish this is outlined white, and that will create a little box, and I can show you over here. Yeah, it's difficult to tell. Let me actually move this. There's a little white box that is appearing here, and I can also make it say, I can make a claim, or I can wish this is, yeah, sure, is labeled. Causal Islands. I can save that and refresh over here. And, oh, okay. Again. Okay, yeah. Now when I refresh over here, it's going to be very blurry, but yeah, you get this cute little box, and it says Causal Islands. So you have, so yeah, this system is a little portable gadget, and with this, the hope is that as we solidify the plans for this, that we've also open sourced the plans for this gadget, and that instead of asking people to set up very large installations, if they want a more portable or easy to set up option, then they can build this sort of small lamp form factor object and take around augmentation with them wherever they go. And that feels like a sort of useful model for replacing how we work. And oh, yeah. So again, Folk Computer is an open source physical operating system, and if you're interested in learning more about setting up your own system, you can go to folk.computer/pilot. And thank you.
Okay, did we all get the fact that the slides were controlled by the computer? Questions?
Hey, thanks for the talk. I was just wondering, how have you seen projector hardware change over time as you've been working on Folk Computer? And are there any kind of technical advances you're excited about coming soon?
Yeah, so when I first started working on or looking into this sort of technology, projectors were very large, and I think that's the biggest sort of part of the most difficult part of this system. We're interested in all sorts of computation, but I think visuals are really nice to give immediate feedback. And so in the last, I would say 5 years, laser projectors have become a thing. And that's actually what this small gadget is running. They're more difficult to acquire, but I think I'm optimistic that in the next few years we will see a consistent supply of very bright, very small, very easy to use laser projectors, and I'm excited about that sort of more portable form factor.
So yeah, thank you, Tui. So the full computer, if I understand that correctly, is it a work like it's not the personal computer, it's the full computer? Is that the idea? And so is the idea that many people can use this at the same time, and there's a bunch of state that this computer can have as well, right? And so has it ever come up that people want to protect some parts of what they would call, well, their personal part of the full computer and that you have to think about, like authentication or some kind of security, I guess.
Yeah, that's a great point. So all the examples I showed today are sort of single player, but the premise of full computer is that it is physicalizing a large shared space, and so multiple people can program in the system at the same time using multiple editors, and everything is global by default, which means that it's very easy to share state as long as you agree on that claim syntax. I could be working on a little calculator program, and you could be working on a little dial interface program or button interface program, and we could hook them together and send both of those things out to the piano program, for example, to make a new program. So the idea is that it's shared by default, and right now it's exclusively shared. We haven't dealt with privacy, but we've thought about having physical tokens that represent your authentication, and either via like NFC or USB drives, or there are sort of some clever schemas for like doing printed out tangible tokens. So yeah, we're thinking about it, but right now the benefits of having everything be global and shared by default outweigh the sort of personal computing burden.
What's the relationship of full computer to dynamic land?
Yeah, so I used to be a volunteer at Dynamic Land. So for anyone who doesn't know, Dynamic Land is a research project started by Brett Victor. And Omar and I met at Dynamic Land many years ago, and I was a volunteer there, so I taught people the language and would give tours. But Full Computer is a completely sort of separate project, and we have, I think we have a bunch of things that separate our paradigm, that integrate sort of traditional computers more closely. Yeah, so we don't have any relationship beyond integration.
Question corner over here.
Yeah, I was just wondering, like, are there like very specific tasks where you go, well, I'm glad we did this in folk because it was much easier and I could do it much faster, or the quality was much higher than any traditional approach?
Yeah, so there's two ways that works out. There's one is like when I find myself using a command line tool a lot, I will sort of think about like, oh, how can I wrap this as a folk program? And so, for example, shutting down a folk system is actually, we have this printed out red piece of construction paper with a full folk program on it, and you have to actually open up a little half fold out, and being able to turn off the system rather than sort of typing an arcane Linux command feels very good, and is also like legitimately useful. Like, I don't have to remember this command, I can just pull it out and sort of remember that it's the big red program. And then, yeah, so there's other things like doing logging or making editing statements. And then there's a whole other class of things like the whiteboard program, where it's just, it feels much it's like much faster to sort of iterate on a drawing and get that state out and make that a full program, rather than having to sort of do something on my iPad, share it to my computer, sequence those frames, and then sort of see that output. So yeah, being able to sort of iterate physically in real time on the table, I think is like another example where folk really comes in handy.
I guess you already touched on that a little bit, but I'm curious if you could talk more about like how you go about debugging things like in the system, and also I guess generally keeping track of your code base, because some of the code, I guess, is physically visible in the space, but then I guess the underlying operating system, like a bunch of like other programs are sort of running implicitly in the background. And I mean, you showed the GraphViz graph, but like that already looked quite quite involved and like quite big and yeah, complex. So like I'm just wondering like how does the debugging story go, and like yeah.
Yeah, so a lot of the time when you're debugging in the system, you're concerned with visibility. So in practice, what we do is that we have programs that print out certain sections of like variables that you're concerned about. There's a very like sort of easy feedback loop, which is like if it's not working, then you sort of can print out specific programs, or sorry, specific variables associated with your program, and sort of see why that state isn't triggering in the background. And then we also do use that first linear statements database and just grab around in that code base to see what statements are getting triggered. And I'm working right now on a much easier way to sort of filter that statement tree to see to only look for specific variables that you're currently working on. And then I think there's like a sort of physical layer version of that we're working towards also, where you can sort of hit a command on the keyboard, and you would be able to see a sort of editor debugging view of all the variables that you've written in your code, and sort of have that automatically projected next to your programs. So that using the sort of physical context and showing you everything we know about the code in real time is like the hope. For the programs that are running in the background, so we refer to programs that are running on the table as real programs, and programs that run in the background as virtual programs. And right now, those are like best viewable via the web endpoint also. But we have plans to project those back out onto physical pieces of paper, and be able to edit those from within the system itself.
I'm curious what the biggest latency bottlenecks are in the system. I haven't tried it personally, but in the videos it looks like there's a significant amount, and I would think that achieving really low latency would be key to getting the feel that you'd really want for this.
Yeah, so I think some of the latency that you saw here was literally just like over HDMI, like my video playing back slowly, and my web page rendering slowly. But on the latency side, I really have to give credit to Omar. He's sort of spent most of the past 2 years working on creating 2 to 3x speedups in Folk. On the side of actually projecting our visuals, that's gotten much faster because we have a custom Vulkan pipeline, so everything is running in a shader, and that actually takes a surprising little amount of time to, once you've compiled everything, it takes a very small amount of time to render. So it actually turns out that the sort of slowest part of our iteration loop is actually parsing the Folk language itself. So Folk is written in Tickle and TCL, which is a language where I like to explain it where if you've programmed in Lisp before, instead of everything being a list, everything is a string. And you might say that feels very slow, and the answer is yes. It turns out it's like about as slow as Ruby, but it gives us the ability to do this like very custom, very literate programming style. And in practice, what we do, we've found ways to run Tickle much faster, and we're constantly working on ways of short-circuiting it and getting our processor to work faster. Yeah. Yeah. Yeah, in the demos you saw, most of them were running on an Intel NUC from 2017, which like has about the power of a PlayStation, PlayStation 2, I think. So yeah, it's not the most powerful PC that's running it. But what that is, we like working within that constraint so that we can sort of know that if it's running really fast in that system, it'll run even faster if you throw more compute at it.
Constraints specific to the hardware, no, like such as like the frame rate, no, of the camera, no, that I guess like, and that kind of like how does that play into musical application, for instance, no, like this limited kind of like refresh and.
Yeah, so there's a bunch of different hardware variables involved in a setup like this. The camera refresh rate turns out to not be super important. Most cameras are operating at above 30 FPS, or 30 FPS or above. We care more about actually higher resolution. So we're working on having faster processing to be able to stream 4K images, and that would allow us to do things like small text manipulation. For the sound stuff, we basically kick all of that to a different backend that's built specifically for sound programming, and so it's able to run on its own clock, and it keeps up with the system.
I want to pull out a bit, because one of the themes of this conference is also like the socioeconomic, political aspect of these things. Not to undermine what you've done, I think it's awesome, and thanks for the presentation. I had a role at Nokia many years ago, which made me go around to all the big tech companies. Spent a lot of time traveling as well. I've seen stuff like this, obviously, in the research labs at Nokia, Sony, you name it. Everybody's been doing this. Digital artists in Japan have been doing stuff like this also, and you're well aware of this, and Brett Victors, et cetera. I'm shaking a bit. I haven't done this in a very long time. The question is, I remember a colleague of mine back then said, it is the business of the future to be expensive. This stuff was happening in those labs because those companies were throwing millions of dollars of R&D research to see what they could do. And we end up with screens and like Vision Pro and shit like that, right? Things have changed a little bit. They have more money, we have less. It's really energizing to see that this is coming out now on the folk level. The question, I guess, is what would you like to see change in the socioeconomic and political situation, where in the end the question was just, you know, what do we need to change, or what would you like to see change in the socioeconomic political situation, where the money isn't just in basically consumer tech?
Thank you. Yeah. So on the material level, like, we're trying to have folk be as cheap as possible, right? Like, the hardware that we run, the software be as efficient as possible, and to have the physical printed artifacts be cheaper and more efficient to run than having, for example, a screen that's always on, right? The only way to do an equivalent thing to this would be to have a giant touch pad that is taking in a lot of electricity just to be idle all day. And yeah, that universe, you wouldn't even get the physical feedback. So I think there's like the sociality part of folk computer is that you should be able to get groups of people together to work on a single shared computational system, right? Because oftentimes you're actually doing a very wasteful thing where you have 30 laptops in a room and you're all sort of real time syncing on a Google Doc, and having to power 30 discrete computers and power the internet that has them all synced together is a wasteful operation for when you're all in the same space, right? So I think being able to build computers that are predicated on physical co-location and systems where you are sharing the burden of being able to iterate on the artifacts that you're working on, I think is sort of the key here. That we're building systems that are useful only for groups of people doing shared work together. Yeah.
This is maybe a good segue and a last question of, this has been amazing. Thank you for bringing and showing it in person to us all. How can this room get involved or support?
Yeah, folk.computer is our website, and you can go to folk.computer/pilot to get a link to our GitHub, where we've open sourced all the plans for our system, and you can download our software and tinker around with it and actually try it out for yourself. And feel free to come up to me afterward, and I would be more than happy to show you the gadget and give you a tour of how we make new programs.